Yeah, let's get started. So first, hello everyone, good morning or good afternoon, and thank you for joining this session where we will be discussing automation, integration, and data management in the context of peak testing. And today it is my pleasure to be joined by three experts in this field. So first, Raphaël Dubé-Demers, who is the CEO and co-founder at EHVA, a spin-off from Laval University in Quebec, Canada. And we also have Antoine Gervais, who works as well for EHVA as a photonics expert. So EHVA develops innovative software solutions to tackle the bottleneck related to peak testing. And Raphael will be our main speaker today, and he will show our EHVA's vision when it comes to peak testing and software solutions to try to make things faster, easier for the end user. So thank you, Raphael, for being with us, and welcome.
Thank you very much. Sorry, I was slow at opening the mic, but thank you guys. It's a pleasure to be here. And thanks for Antoine as well. We are a team, we work together. So I thought it would be interesting to be all together. I'll let you,
Yep,
Mathieu.
absolutely. Thank you, Antoine. Yes. And we also have Laurence van der Vet on the call. So Laurence is a subject matter expert at EHVA, and he's based in California in the US. So Laurence has been following the peak very closely and involved in this domain for the past decade. So hello, Laurence, and good morning.
Good morning. Good morning, team.
And myself, so I'm Mathieu Bergon, product specialist at EHVA, and my main focus is on solutions for passive component testing, so whether it's in the lab or manufacturing. And peak testing is quite relevant in this for passive testing. So this talk will be around 30 minutes, so that will give you an opportunity to jump from this session to another session of your choice. So we have two other sessions in parallel, one about next-gen component testing and another one about peak-based transceiver testing. So make sure to go on the EHVA event platform at the end so that you can attend these sessions afterwards. This session will be recorded and available on demand from the EHVA platform as well. And without further ado, let's get started. So when it comes to peak testing, so we all know that the test stations are far more complicated and complex than for conventional, purely optical testing. And quite often you will find a wide variety of instruments in peak test stations. So we have here on the screen different elements, such as the wafer probe station, where you will put the wafer. You have a whole lot of test instruments, whether it's optical, electrical, or for RF testing. So you may have some or all of the above. You will have motion systems, actuators, vision systems, a bunch of sensors, proximity, temperature, and so on. And obviously all these instruments, all these different parts need to operate as a whole, as a complete system, so that from the end user's perspective, it appears as a turnkey and easy to use solution. And this is where the need from a control software comes in. This control software will take care of driving all the different pieces of the puzzle in a fast and reliable manner. And this is what we will be discussing today. Obviously, this is achieved through automation and integration. But if you take a step back, you quickly come to realize that the whole picture is not only about automation and integration. There is a lot more than this when considering the software solution that you want to use with your hardware setup. So basically, automation and integration enables you to drive your instruments quickly and reliably, and it will give you a lot of data. But then you want your software solution, just like your hardware setup, to be modular and evolutive over time. Your test station will not be the same in R&D and in production, and so will your software solution. So it does need to be modular and evolutive. You want your software solution to be able to provide you easily KPIs so that you can monitor your process. And you also need a solution or structure that is able to handle the large amount of data that you will be gathering during your test. So it needs to be scalable, and it also needs to be shareable, because we've seen that many companies need to work together to have a complete test solution. So you need to be able to share these test results with your supplier and with your customers. So something quite important about data is, being able to store the data context, and you want to do all of this. You want to ensure data integrity and data traceability. And finally, I think one key point that Raphael will touch more on is about gaining insights from your data. You want your measurement data to enable you to improve your process, to improve your design, so that over time, the whole process gets better and better. And with this quick introduction, I will hand over the mic to Raphael, who will give you more detail about EHVA and EHVA's solution.
Yeah, just a quick note before Raphael starts to do his thing. This is a note for the audience. I mean, we want to make this this session as interactive as possible. So don't be shy. I mean, feel free to raise questions as they may pop up during Raphael's presentation. Again, don't shy away, but bring it up. I mean, there's no such thing as a silly question, and we're here to help you out with any questions you may have. Okay, with that, over to Raphael.
Definitely. So hi, everyone. I'm super glad to be here. I'll share my whole screen, actually, because I have a few things to show. And as Lawrence just said, yeah, I would be super happy to have questions. And for us, it is not super trivial to explain everything we do because we have a specific amount of time. So I'm here today with Antoine as well, which will be presenting. So EHVA is a super nice startup company that is a little bit more than 2 years old from Université Laval. What you see here is our main team, although that's not true because we are growing bigger as of today. And today we will focus on the software, but I just wanted to say EHVA is also offering a complete hardware solution. So what you see here is our main 300 millimeter wafer testing platform. But the idea is we've made something that is basically able to test electro-optical components from simple things like module up to complex things like wafers and even diced wafers and multi-die and so on, right? So our station are always, and the whole software, electro-optical measurements. So basically not just the optical side, not just RF, but really all the things. So our station, they handle natively up to 4 probes on the cardinal points. But software-wise, what we've done is something very advanced, and we are really proud of what we have, because what we realize is if you want to drive very complex stations on very complex devices and do very complex tests, and overall view is needed, and you want to analyze and understand basically what happened to generate next iterations, product yield engineering, things like that, you need actually a lot. And when we were looking around, we did not find the right solution. So to give you an example, I'm trying to walk the wheel of how our software is designed by using this specific example. So that's the chip that we are testing in the lab. It's one of our design. And what we see are basically electrical pads and optical IOs. So these are standard grating couplers. And that's the starting point of our system. The system understands the devices. So basically for this system, a device is more than just, coordinates of IOs. It is also a relationship in between them and the component, and about basically the component itself. So when we look at the hierarchy, we have a wafer that is made of reticle, that is made of die, and all of these dies are made of devices. But what we don't see here is that all these devices, eventually they live in the environment, and the environment is made so that we can basically add for instance, process information to it, assembly information to it, results information to it. So at the end of the day, it makes for a very complete system that will give traceability, component library, and basically the ultimate control on what happens. So the idea here is to say, with this environment, we can test a complete wafer. We can have it diced somewhere, can go at somewhere else, like a contract manufacturer, for instance, that will do the die testing in the assembly. And at the end of the day, we have the capacity to perform analysis, business intelligence, and basically the overall, again, control and ownership of this data chain and information chain within the software. That's the idea of it. And another big part of the automation that we've made is the sequencer. So basically, we assume now we have devices that are known to the system and we want to test them. Well, how do we do that? And how do we respect basically the foundation of what we thought is necessary, like open instrument control, analysis, and so on? Well, that's what I'm going to show you right now. And here, I mean, I would be super happy to have questions because that's the whole purpose of the.
Well, I have one, Raphael, on the sequencer. I mean, how is that data or configuration file stored? Is that stored as part of the data file on the device that's been tested, or is this a separate file? Because, you know, at the end of the day, of course, you want to, you know, maintain and keep traceability on whatever process you've followed to characterize a specific device. So can you tell me on how that is done? Is that part of the same file or two separate files with a common denominator?
Yeah, thank you, Laurent. So basically how it works is that everything is centered around what we call a data store that is a cloud-based, you know, data system. So at the end of the day, it's how we phrase the question that is maybe in question here. So assuming we design devices and then we feed them in the cloud, underneath it's many different tables that describe what the device is, and the sequences at this point, they are not yet linked to any component. That's actually the idea, and that's where it goes, right? So basically at the next phase that we call the test plan phase is where we link devices to sequence, because as I will show in the sequencer, the whole purpose of the environment is to create things that are modular and reusable. So for instance, the sequences, they are not tied to any object per se. So that's an example of the measurement sequencer. Its goal is just to produce test logic in an open cloud-based scheme where people can share and work. So on the left pane, we have the instrument side, which is basically a collection of all of the instruments that we can find on a station. So it allows us, for instance, to represent and publish a station to someone. And as you can see here, we have vision system that will have methods and properties. If you hover over them, you have the signature of the functions, things like that. We have the motion system, like two of them, an Aerotech one, a Smaragd one. And then we have, for this station, an EHVA equipment, the CTP10 platform with a laser. And again, it has full of methods, full of properties that you can use to basically do the sequencing and the creation of the test. And then a simple Keithley SMU, which is also standard here, right? So how this works is super simple. The instruments, any properties or method is just drag and drop to here to basically build the sequence. And when we say how it is open in an environment, basically we can just add driver or libraries to it, and they will be reflected here in the instrument. So it allows us to basically build the community that is ever stronger. Universities, people can participate, vendors, equipment vendors can participate, and basically private customer equipment like custom test PCB can also be used directly in this environment without, you know, much work. That's basically the same story for how the sequences work. So these are basically sequences. If you look at one like, for instance, this one, right? That one is basically a sequence that is used here in this master sequence as a child sequence. And the environment is able to know basically what are the ancestors, basically the sequences that are using this one. So the whole traceability is there. The mathematical box is actually more than just mathematics. It's a little bit like the instrument, only that they don't have any connection to anything. So basically we can add library, reference library, and these could be simple, you know, things like a constant, right? So I shall have used like fields. So just constant, but they could be computations, and they are eventually, I wanted to keep it simple, but numerical vision and AI libraries of computations and so on. And it's also a plot library, right? So at EHVA, we've developed our own plot scheme and so on that could be reused, save as you go and so on. And then if we look at the sequence, we can have a complex branching. So like here, it's a for each. So all of the usual programming, logical structure are here. And the data interaction is here. So basically what we will say, for instance, here, if we look, is that we will say, I'm going to save a result. And this result will have the name trace data sweep. It will has as a value the variable trace data sweep, and the description will be that one. So at this point, I just created the sequence that will execute manipulation and archive the results in the data system. And basically, when I am executing the test, that's only when the binding in between the component is happening. So basically, we can have domain, we can have experimental conditions, we can have computed results, and all that stuff. So it's really advanced. And again, I would be happy to go more on that if you have questions. But the idea here, for instance, is to scale fast and clean. So for instance, you have a photo detector. You will do IV curves, you will do things like that. You just basically build it and that's it. And now how the environment is advanced, well, not only we have capacity to comment, things like that, cut and paste sequences and so on. The sequences, they have inputs and they have outputs. So basically, that's how they can be nested into complex trees. We have what we call an active aligner optimizer. So it's basically, so if I click on it, I won't save the results, but if you look here, basically these 3 lines, it takes a feedback function, which could be any function that will return a number, takes a flavor, which is basically the optimizer strategy that we use. That is a library that we have here. And then an action function, which is basically a sequences that will take a vector as an input that will be basically on what variable do you do the alignment. So it could be a 2D alignment, it could be a 4D alignment, it could be based on electrical feedback, a compounded electrical and optical feedback. It has no limit, right? And we also use it for things like maintaining, you know, a specific transceiver on its transfer function while we do BER measurement, for instance. And how we do that is because we combine the notion of generic optimization with basically, I'm looking for it, yeah, parallel threading. So basically we can tag sequences to be executed as parallel sequences. So basically sequences that would monitor the status of a chip or a device when we do the actual test, for instance. So that's pretty much it for the sequencer. And then we just edit the sequence name, blah, 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 and we save it. It's how it works.
So question here, Raphael. Yeah. I'm thinking about, you know, you mentioned a community. I mean, this is data and information that is being shared among, you know, multiple parties, you know, in certain instances. How is my IP protected? That, you know, whatever device that I've exotic design I've designed, I want to make sure that the IP intellectual properties, they stay within my organization and is not accessible by any third party. So how is that protected?
Okay, very good question. So the idea is that what we've developed and what we provide is an implementation architecture. So basically, it means that at the end of the day, when you connect to the data system, you can either say, I'm going to use a database that is private to me, so your IP is protected because it's your environment, and it could be hosted in the cloud or on-premise. So first way to protect it is own it by yourself. And then the community notion basically means that we can have different accounts that are located at different places on different schemas with different users. So we have the complete freedom to manage what we call the data replication, and we have basically a data policy access. So basically access tokens that will say to people what they can basically see from other and what they can give to other, right? So it's completely transparent and it's customizable. So it's not, well, I disconnected, right? But yeah, it's how it works. So it's à la carte, basically, I would say.
Okay.
So, okay, and the execution, that's the same kind of thing. So once we've done basically devices, sequences, and we've said the test plan is basically all these logical definition of devices will be grouped with these sequences and so on. We go on to execute this. And what Antoine will show you is the station itself, the execution environment itself is dynamic. So we can define what the station is, what the probe is, and the software will autonomously manage to fill out the requirement and define the right movement profile and use the aligner that we've defined in the sequence to do that. So it's super dynamic. It is remotely operable. It is super easy for an engineer to basically build a test flow and then distribute it on many different stations. It is easy to scale the station. And basically, it's also super good for large data and basically any throughput. So what we will show today, what Anton will show is basically this very station that is sitting next to, where we have actually a chip that is being tested with a DC probe. That's an adapter for a single die, and it's a fiber array, things that people know. And we have the EHVA equipment, so basically T100 laser, a CTP10 component tester platform, and the EHVA optical switch as well to basically operate this. And you also see a polarization scrambler, SMU, and the controller for the motion system. So yes, Anton, I think it's...
Okay. So basically, I'm now connected to the station application, and we will execute the sequence that Raphael showed. So first, we need to load a station configuration, which includes all the instruments. And we have different graphical user interfaces that bounce to the instruments, the camera, the motors. So for example, I can connect the camera, get a live feed,
So what's magical here, I mean, the key point is that a camera is a camera. It has signatures, and the environment is able to use any one of them. Same for motion system and so on. So it's really, really advanced, actually.
And now we have this ring resonator that has thermal heaters, and by connecting to the SMU and the CTP10 mainframe, you can then select the sequences that was shared across the database. And what this sequence does is acquiring optical sweeps over different biases, over different voltages level of the ethers. So,
and maybe a comment, I mean, what we see here, the delay is because we wrongly use the CTP10. It's in like PDL mode, so it does 4 sweep per measurement. And we've made like few pauses, right, just to make sure everything would go smoothly. But we see the ring shape and so on. So.
And now we should have these optical spectrum at levels of 0, 2.5, and 5 volts. And we can interact with the charts. It automatically also saves the results in our database, so we can access this later. And it's already done and completed.
Fantastic. And basically at EHVA, we own every aspect of the software. So basically even the plot here is just a simple one, but we are soon to release a very nice real version of plotting and so on. So if I may, I will reclaim the screen. Antoine, it's okay. So I'm assuming that people see my screen correctly.
Yep.
So one of the other big part of it, aside from machine vision, AI, and so on, is really the data analysis. So again, what we thought is when you take measurement, like the ring that Antoine just shown, we can easily add in the mathematical box, things to extract the peaks, basically figure of merits. But at the end of the day, even if you do that, sometimes you need compounded analysis, and you need more than that, a scalable, flexible way to consume the data. So what we've done at EHVA is that we've built our own, scripts and analysis for key things that lives in the cloud. But we also have connector for MATLAB platform, Power BI platform, and that's the one I'm going to show you after, Excel platform, RStudio platform, Jump from SAS, and Python. So basically, we have direct ways to interact with the data. It's a two-way, right? For all of it. And at the end of the day, we can generate, so it's a customer example, it's a real world example. We've tested a lot of things. We had, test parameters, some component definition, even some tooling, right? Or here it was a spring that had been characterized with, it's a constant, stretching factor. And we were basically able to produce deterministically, the correlation matrix in between all of them, the statistical significance of all of them, and basically directly pinpoint what has been undersampled, oversampled, and what were the few main tendencies. And we basically changed the yield by like a factor of 5 just by doing that. So what I want to say is that is part of EHVA's system.
Okay, I think the idea is that it goes into a database, and then the end user can really extract and visualize and compare, do some analysis with all the data that is within the database.
Yeah, definitely. And here it was just to showcase like a simple results viewer. So it's directly connected to the database. If we want, we can show like the last one that have been taken. So these are the one that we just took live here. And yeah, that's basically the idea, right? And then we could see experimental condition, what happened, for instance, when we just had the 0 bias and the 2.5 bias, and we see basically the progression of the spectrum. And yeah, that is it. Thank you.
And with this, I will thank everyone, participants and presenters, for attending this session. Thank you very much.
All right, thank you.